And to look at the proof, we have to switch to the proving perspective. Before that, let me draw your attention to the name of this proof of obligation. It's systematic. It's to do with the withdrawal events with action 1 specifically over here, right? With action 1. That's why the label here is so important. And then it has to do with something called WD. When we saw the IMV, it has to do with the invariance. But when we see WD, what does that really mean? It's something to do with the well-definedness, which I will explain to you in a moment, right? But every time if you got any proof obligation that cannot be discharged, you should always look at the name of the proof obligation. It's named systematically so that it's convenient for you to trace exactly where the problem is. All right. Let's now go to the proving perspective. Well, let me double click on this first. Double click on this proof obligation, and then you can see it's open over here, the tab. However, we want to switch also to the proving perspective over here. So once we do that, that's what you'll see. I would say whenever you want to see exactly what's being proved, since the proof actually fell, right? You can see there is a proof tree panel over here. It's a very important tip over here for you. What I want to do is not to really see the intermediate stage of the failed proof by the prover. What I really want to see is the initial configuration or predicate that the prover was attempting to discharge in the first place. How do I do that? All you need to do is go to the root of the tree on the top over here. That's basically what initially is supposed to be discharged over here. We'll talk more about how to analyze the proof tree later. But for now, let's now make sure we know how to look at the very initial predicate that's supposed to be discharged but actually fell, right? If you look at that over here, if you click on that over here, you can see that's the very original one that's supposed to be discharged. If you actually want to start from scratch for some proof, what you can do is you can right click on this and then you simply say prune over here. In that way, that will allow you to actually interact with the prover from here, from this points. So we got rid of all the intermediate proof that actually fell, right? Let me just save it just for now. Okay, you can say okay to save. Of course, we're not going to prove it for this lab. Once we fix the model, once we see what the problem is and fix it, it should just be discharged automatically. But we're going to see what the problem is. So make sure you know how to prune the tree and see the original thing that should be proved, right? So I'm going to take a screenshot of this guy over here, and I'm going to show you exactly what's being proved and how we can fix it. All right, let's now switch to iPad over here. All right, just to show you that this is the withdrawal event that we specify, right? With the two event parameters, with their timing constraint, and also with the two actions over here. And the proof obligation that we're talking about is about withdraw, Act 1, and also WD. And as I said before, WD is something called well-definedness over here. Okay? Well-definedness. And usually has to do with whenever you try to apply some mathematical operation, the precondition of the mathematical operation should be satisfied. Okay, it's about the preconditions of mathematical operations being satisfied. That's to do with the well-definedness. All right, it's really important. And then let's now identify exactly where we should look at. We should look at withdrawal, which is exactly what I'm trying to focus on. And specifically, we want to look at action number 1. So we got some well-definedness issue for action number 1, which is this one here, right? That's very good because now we can narrow down the search space. We don't need to worry about, for example, action number 2. That's not a problem, right? Only action 1. And then what's happening over here is, remember what I said before over here. If you actually want to do this expression over here, it's basically over here. This will be equivalent to that relational overriding. Let me write it down, but just for your information. So this is BA. So B is overridden with this particular mathematical notation, order pair. So that will be A, the accounts over here. The account over here maps to B A minus V, right? That's the corresponding math notation. However, if you look at this, right? If you look at this particular expression over here, so now let's say what might go wrong over here. Whenever you want to make a function application, this is a function application. And you can look at your week number 2 lecture to see what a function application is, right? Function application. And it's should be obvious, and also maybe you know that already. The function application has a precondition. Because we cannot just simply got undefined, right? In that case, A must be in the domain of the function, right? A must be in the domain of that function B. That's the something that we want to make sure, right? So that's exactly what we're having over here. That's exactly what we are trying to prove over here. So A should be it should be a member of domain B, right? And also, there's another one over here. By the way, this one over here is actually something to make sure the invariant is also maintained, right? Remember we said before, every event must also maintain the invariance, right? So this is to make sure after this particular action over here, you maintain this particular B to be still a partial function between account and integer. But this is not the issue over here. Let's focus on this. This one is not being discharged. And this one is saying that what will be the hypothesis we can use? You can see we got go over here, and also we got these two are the hypotheses that we can use to prove the goal. HYPO is hypothesis, right? So overall, this is what we want to prove. If A is a member of the accounts, any account, and V is a positive number, that should imply, that's what the Rodin was trying to prove. A is actually a member of the domain of B, right? And this must be proved, otherwise the function application over here wouldn't make sense, would be undefined, right? So now, what's wrong over here? Well, somehow this cannot be proved. I can tell you that it should not be proved somehow. And this is the well-definedness constraint over here, because you're trying to do function application over here, and the precondition for that is A must be a domain of the function. So that's where the well-definedness actually came from. Just make sure I understand what the problem is. All right. Somehow the hypothesis is not strong enough to entail the consequence over here, the goal. All right. You can now pause the video and think about it. All right. Assuming that I thought about it. Okay, it has to do with this particular hypothesis, this one specifically. Why? Let me now talk about if you recall one of the diagrams I drew, if you pay special attention to what I said before, maybe you did, but you maybe just forgot. Okay, let's take a look. Remember this diagram I drew over here, right? I said the account is a carrier set, which includes even those accounts that may not be active. If A is only a member of account, in that case, how can you be sure that A at the runtime that might possibly be the case over here? If A is being used to really inquire the balance, then it will be undefined because A is not active. It's not in the domain of B, right? So really refer to this particular diagram. I want to really maybe I will do you a favor of maybe just copying this. I think that'll be very, very useful for you to review this diagram over here. That's really the essence for that particular proof obligation. Okay, let me just go to this particular part over here. Okay, over here. All right. I think one tip for really succeeding this course, you're gonna be very patient about knowing about what's really available there in order to prove something, right? Just bear with me about presenting to you the details. Okay, so this diagram over here is something I want you to remember over here. Okay, so this is the active accounts. All right. So what would be your suggestion to really make sure the A over here cannot be simply a member over here, because there happen to be this member here is not in the domain of B, in which case B of A is undefined, which will violate the well-definedness condition. Well, why don't we make it stronger? We want to say not only that A is a member of the accounts, but also A should be a member of the domain of B. That'll be the simplest way to fix it, right? So now I got two choices. Either you can simply modify this to be maybe the just say domain of B. That'll be one option there, right? Or you can simply just add another guard to say A should be a member of account and A should at the same time be a member of the domain of B. You got two choices, right? Either way is okay. Let me just maybe change, maybe just add another guard. How about that? All right, let's now, okay, hopefully you now can see that, okay? So the fix over here is add another guard, which will be A is a member of the domain of B. In that case, it will be trivial, right? Remember, we spoke about some tactic called goal in the hypothesis. If you want to prove this goal, and the goal is already in the hypothesis, in that case, we can prove it, right? In this case, it's actually reasonable to add this constraint. Apparently, whenever you want to withdraw some money, you want to make sure that account is really the active account, rather than some arbitrary account name. Okay. Let me now go back here and then fix it. All right. Let me now simply go back to event B, and then I will go to let me close the proof over here and go back to bank 0. I can, as I said before, you can either just modify this to be the domain of B, approach 1, or you can simply just add another guard. Under the where, I can say add guard over here. Let's say WD for I'm just making some label over here for B of A, right? It's a nice label over here just to make sure we understand. In order for BA to be well-defined, for the well-definedness, we want to make sure that A is actually is a member of the domain of B. All right, over here, this is really needed. Okay, and save. Well, everything is proved.